Okay, so yesterday, where we left off was, so we are trying to solve basic exponential equations, which means the bases are related, okay? So as you can see, in most cases, the related bases will mean equal bases, but you will see that that's not always the case on some problems. Okay, so once you set bases to be the same, you can then set exponents to be the same as well. Okay, and in particular for this part A, so what you have to do here is first writing 27 in terms of the other number 3, which is 3 cubed, and then you just use another rules of exponents, which is this multiplication of exponents, and then set 3x is equal to 1, which is the invisible exponent, and so x is equal to 1/3, okay, which was rather a simple number, okay? And as you will see, for these basic exponential equations, your answer will be pretty simple, okay, either whole numbers or very simple fractions, okay? So if you get something like this, like 134 over 321, okay, then you should immediately know that you have done something wrong, okay? So you won't see any like complicated looking fractions. Okay, so now part B, 5 over 2 to the power x is equal to 4 over 25. Okay, so here the two numbers that we are dealing with are, I guess unfortunately, and I guess some of you might cry, the fractions, right? 5 over 2 and 4 over 25. Okay, so yes, we have fractions, but look at these two fractions and can you see whether they're related or not? Okay, so yes, apparently 4 and 2 seems to be related, and 5 and 25 seem to be related, right? Okay, so the first step is, let's try to write 4 over 25 in terms of maybe 5 and 2, okay? So here at this point, we don't see 5 and 2, but this means what? So 4 is 2 squared and 5 is, or 25 is 5 squared, right? Okay, so what does that mean? We have 2 squared over 5 squared, so that means it's the fraction 2/5 squared, right? Okay, so now we have 5 over 2 to the power x is equal to 2 over 5 squared. Okay, so now we have these two numbers, 5 over 2 and 2 over 5, and they're not the same, right? Okay, they are not the same, but are they still related? Okay, so they are not the same, but they are what? So-called reciprocals, right? Okay, reciprocals. Okay, so now, what does that mean? So for example, let's look at some simple number. So let's see, maybe 1/2 and 2. Okay, so now these are what? Off by -1, right? Okay, now what does it mean by off by -1? So off by -1, and what does that mean? That -1 is in the exponent, right? Do you see that? Okay, so in other words, 2 to the power -1 is 1/2, right? Okay, and similarly, 1/2 to the -1 is 2, right? Okay, so these are related by -1 in the exponent, right? Okay, so what does that mean? So from here, 5 over 2 to the x is equal to 2 over 5 to the second power. So they are reciprocals, which means these are off by -1 in the exponent. So what do you expect to happen in terms of these two exponents? So first of all, x is not equal to 2, right? Okay, so how should you say? So from here, either what you can say is negative x is equal to 2 or x is equal to -2, right? Okay, because the negative sign can go in front of x or in front of 2, right? But not both, right? Okay, so no matter which equation you choose, what's the value of x? It's this one, right? Okay, so again, what you have to make sure is when you have the reciprocals of the two numbers, then they're off by -1 in the exponent. So what you have to do when you set exponents equal to each other is include the negative sign on one exponent only, not both. Okay, so the answer is -2. Okay, so now that's B. And then C. 2 to the power 3 minus 2x is equal to 8. Okay, so now the exponent is not just x. It's some kind of expression of x. Okay, and here, which two numbers are we looking at? Not 2 or 3 or 2 and 2, right? Okay, we are looking at which two numbers? That 2 and that 8, right? Okay, so here, again, are 2 and 8, okay, these two, are they related? And the answer is what? Yes, right? Okay, I mean, not 8 equals 2 times 4, but in terms of the exponent or exponential form. So 8 is equal to what? 2 to the what power? Third, right? Okay, so what do you have? 2 to the 3 minus 2x is equal to 2 cubed, right? Okay, so now do you have the same basis? Yeah, okay, so these two are the same. So that means what should be the same? The exponents should be the same, right? Okay, so solve this equation. So subtract 3. Okay, so that means you have -2x is equal to 0. Divide by -2. So x is equal to 0 over -2. And what's that equal to? -2, 0, undefined. 0, right? Yes. Okay. Okay. So now that's that. And now part D. Okay, so here comes part D. Okay, so now part D is kind of important because this one requires a little bit of trick and fact, which you have to know as well. So 27 to the power x is equal to 1 over square root of 3. Okay. So now here, the two numbers that we have are 27 and 1 over square root of 3. Now, let's focus on this 1 over square root of 3. So even though we have a fraction here, the thing that we especially focus on is square root of 3. Okay, so is 27 and square root of 3 related? And usually that gives people a little bit of trouble. So let's go even more basic. Is 27 and 3 related? And for that, people usually can answer pretty easily. And the answer is obviously yes, right? Okay, yeah. So let's look at 27 and 3. Okay, and here 27 is 3 cubed. Okay, so now, then 27 to the power x will be 3 cubed to the power x, and that means we can multiply the exponents. So we have 3 to the power 3x on the left-hand side, right? Okay, and this is not hard to see. Now, what is the key on this problem is this 1 over square root of 3, and in particular, square root of 3. Now, we need some kind of exponential form. So, can you express square root of 3 as 3 to the some power? And what should this exponent be?
Would it be negative?
Say that again.
Would it be negative?
Negative? Not yet, but eventually, yes, we will have the negative sign, but not here. So here is my first hint. Any idea? So like, don't say 2. 3 squared is not square root of 3, right?
Is it 1/2?
1/2, yes. Okay, and what's the reason? Here is another exponent, which is 1. So we have 1 over 2. Okay, so you must remember this conversion. Square root of any number is that inside number to the 1/2 power. Okay, so please remember this conversion. That might appear not only on your homework, but somewhere else. I don't know. Okay. Yeah, I'm just kind of stupid, so I cannot say that word. But anyways, so square root of 3 is 3 to the power 1/2. Okay, so what does that mean? Here is another conversion. Now we have 1 over square root of 3. Okay, so we have 1 over 3 to the power 1/2. Okay, now remember, let me go up a little bit. Okay, so when we had like 2 to the power negative 2 from yesterday's class, we saw that's 1 over 2 squared, right? Okay, we saw this conversion. So now, what does this mean? That 1 over 3 to the power 1/2. This is 3 to the what power? And now we have to go back to Kendra's answer, the negative sign. Okay, so it's negative of what? 1/2, right? Okay, so we have 3 to the power 3x is equal to 3 to the power negative 1/2. Okay, so that 3 to the power negative 1/2 is the exponential form of 1 over square root of 3. Okay, so now we have the same basis. So that means the exponents are the same. So 3x is equal to negative 1/2. Okay, so divide by 3. Okay, so now we have negative 1/2 all over 3. And what is this fraction equal to? Negative 1/6. Yes, do you see why? Okay, 3 over 1, and then you flip the bottom right. Okay, so this is negative 1/2 times 1/3, so it's negative 1/6. Okay, so another misunderstanding that people make is, okay, so that means whenever we have the square root, we'll have the negative exponent, and the answer is no. Okay, why not? Because what if we had just square root of 3 on the right hand side? Okay, not 1 over square root of 3. Then we won't see any negative answer, right? Because then we'll have just 3 to the power 1/2. And so the answer would be just positive 1 over 6. Okay, but only when the square root is in the denominator of a fraction, then yes, we'll see the negative sign, but otherwise we won't. Okay. So that was kind of hard problem. And now part E. Okay, so now guess how I can pronounce this part E. E to the 3 minus x is equal to e to the 3 minus x. Same thing, right? Now, so even though, yes, the way we say is the same, are they really telling us the same thing? No. Why? Because for the left-hand side, it's e to the 3 minus x, right? What does that right-hand side mean? Does that mean that like little horizontal line thing is the subtraction? Or is it something else? No, it's the negative sign, right? So clear parentheses on the right-hand side. How?
Multiply the exponents.
Multiply the exponents, yes. Okay, so the first thing that you should notice is the right-hand side. Okay, it's not, oh, well, yeah, you can say that it's e to the 3 minus x, but it's e to the 3 times negative x, right? So it's e to the negative 3x. Okay, so you have e to the 3 minus x is equal to e to the negative 3x. So indeed, they are not the same. So parentheses matter, right? Okay, so here we have the same basis. And by the way, from yesterday's class, that e represents what? The natural number. Remember that? Okay, and it is a legitimate base, right? Okay, so now what do you have? E to the, no, 3 minus x is equal to negative 3x, right? Okay, so here, what can you do? Maybe add x. So 3 is equal to negative 2x. Divide by negative 2. So what's the answer? X is equal to negative 3/2. Okay. And now F. Okay, so now here comes another somewhat tricky problem. 27 to the power x plus 1 is equal to 9 to the power x minus 3. Okay, so now what do you notice here? So far our exponents were pretty simple, either x or some kind of expression of x, okay? And we didn't see like multiple expressions of x. And now this time we have x plus 1 and x minus 3 as the two exponents. And here there's another weird thing. So what we are looking at is what? 27 and 9, right? So now, is 27 and 9 related with each other? So yeah, 27 is 9 times 3, but remember, that's not the point, right? Okay, because we are not talking about the multiplication. Okay, in other words, here 27 is not 9 to the some power, right? Okay, we cannot write like this. 27 is not 9 to the some power, right? So are we in trouble? So you have to ask deeper question, which is what? So 27 cannot be written as 9 to the some power, but are they coming from some common number?
3.
3, yes, right? Okay, so 27 is not 9 to the some power, but 27 and 9 both come from 3. Okay, so what does that mean? 27 is 3 cubed and 9 is 3 squared. Okay, so what do you have? 3 cubed to the power x plus 1, and then 3 squared to the power x minus 3, right? Okay, and now clear the parentheses on the left-hand side. What does that mean?
Multiply the exponents.
Right, and same thing on the right-hand side as well, right? Okay, so 3 to the 3 times x plus 1, and then is equal to 3 to the power 2 times x minus 3. Okay, so we have the same basis. Okay, so now if you want, you can say, oh yeah, we can cancel like this. It doesn't really matter. And then here we can distribute 3 and 2. So we have 3x plus 3 is equal to what, 2x minus 6? Okay, so here what does that mean? Minus 2x and then minus 3. So what do you get? X is equal to negative 9, right? Okay. Okay, so now that was F. Okay, so here what you can see is the basis being related not only means that you can express one number as the other number to the some power, but also these two numbers may come from the same number. Okay, so that's what I mean by the basis being related. Okay. So that's F. And then go to, can I go to the next page? Yeah, okay. So now G. 1 over 49 is equal to x to the power negative 2. Okay, so now here, what can we first do? So here the issue is what? The negative exponent, right? And yesterday we saw that negative exponent is kind of not okay because that gives us hard to identify what the true base should be, right? Okay, so can we possibly rewrite that x to the power negative 2? So how can you write x to the power negative 2 so that we don't have the negative sign?
It'd be 1 over x to the second power.
1 over x squared, right? Yes. Okay, so x to the power negative 2 is 1 over x squared. So we have 1 over 49 is equal to 1 over x squared. Okay, so now we have the equality of two fractions and maybe something like that. The so-called butterfly multiplication thing or cross multiplication, which is the way I prefer. Okay, so what does that mean? 1 times 49 is equal to 1 times x squared, right? Okay, so this means x squared is equal to 49. And so now what does that mean? We can take the square root, right? So x is equal to what? Say that again?
7?
7?
Plus or minus 7.
Thank you. Plus minus 7. Okay. So 7 and negative 7. Okay, so now here, what gives trouble, like I guess some kind of time to consideration, I guess, for some people is this number okay? So yesterday we saw that the base cannot be negative. Let me see if I can pull that out right here. Okay, so the base is always positive. So is negative 7 out? And how do you tell whether that is truly a base? So X is where? Here, right? Oh, so that is the base position. But here, what is the issue? That, right? Okay, we have negative exponent. So what does that mean? X is not the base, right? Okay, so what does that mean? Oh yeah, negative number is okay because that's not the base, right? Okay, and here X is what? Here in the denominator, okay, and then we have square here, right? So what does that mean? Yeah, negative number is possible. Okay, so this is not out. So the answer is plus minus 7. Okay, not just 7. Now, once we go to the next section, yes, you'll see a problem where the negative number is not possible, but not here. Okay, so be careful with the true base. Okay, and now H. Oh, look at H. We have that another kind of evil object, right? Which is what? The square root. Okay. Now, yes, it is kind of hard object, but at this point we know the conversion, right? Okay. So the two numbers that we are looking at are what? Square root of 3 and 9. And they seem to be related. And if you cannot see the conversion, just ask simpler question, which is what? Are 9 and 3 related, right? And the answer is obviously yes. Okay, so here 9 is 3 squared, that's obvious. And square root of 3 is what? 3 to the power 1/2, right? Okay, again, I told you to remember this conversion. So we have 3 to the power 1/2 to the power x plus 4 is equal to 3 squared to the x, right? Okay, so that means we can multiply the exponents. So we have 3 to the power 1/2 times x plus 4 is equal to 3 to the power 2x. Okay, so bases are the same, so we can just set exponents equal to each other. Now here, we will distribute 1/2, right? So what do you get? 1/2 x, I'm losing my ink. So that's okay because I have a new pen. So 1/2 x, and then 1/2 times 4. What's that equal to? 2, right? Yeah, so plus 2 is equal to 2x, right? Okay, so what does that mean? We can subtract 1/2 x. Okay, so we have 2 is equal to, what is 2x minus 1/2 x?
Three half.
3 over 2x, right? Yes, okay. And then what do you do? Divide by 3/2, right? Okay, so we have 2 over 3/2. What is this equal to?
4/3.
4/3. Do you see why? 2 over 3 times 2, right? Okay, so it's 4/3. Okay, you may see fractions, okay, even in these exponential equations. So yeah, remember fractions have to be your best friend, not only your friend, okay? So now the last problem. 1 over e to the power negative x plus 1 is equal to 1 over e squared to the power 2x minus 5. Okay, so apparently this looks terrible. This looks awful. Now, here we are looking at 1 over e and 1 over e squared. Are they related? Okay, how? So here, what can we do so that we have the same base?
Square the first e. Square the first fraction. Well,
Square the first fraction? Okay, now the problem is if we square like this, to match the balance, we have to do this one. And so we'll end up with another different basis. So I guess my suggestion is, can you possibly rewrite what's inside parentheses so that we don't see any fraction? Is that possible? So 1 over e, rewrite this so that we don't see any fraction.
Multiply each side by the negative 1 power.
Right? So 1 over e is e to the power negative 1. Okay? And then 1 over e squared is what? E to the power negative 2. Okay? Then what do we have? E to the power negative 1 to the power negative x plus 1 is equal to e to the power negative 2 to the power 2x minus 5. Okay, and now what does this mean? We still see parentheses, but at least we now know what to do, right? Which is what? Multiply the exponents. Okay, so instead of having 1 over e or 1 over e squared as the common base, we have to have what? E as the common base, right? Okay, so these two are the common bases. And so we can just now set exponents equal to each other. Okay, so now we have negative of negative x plus 1. So that means what? X minus 1, right? You can just switch the signs, right? And then we have what? Negative 4x plus 10, right? Okay, so here what do we do? Maybe add 4x and then have to add 1. So 5x is equal to 11. So x is equal to 11 over 5, which cannot be reduced, right? Okay. So again, the point of these problems is making the same basis. And in order to have that, what we will end up is either express one number as the other number to some power, or both numbers will come from the same common number. Okay, and like I said before, all of the answers are either whole numbers or fairly simple fractions. Well, I guess there could be some dispute that some people think 11 over 5 is not a simple fraction, but I guess it's way better than like 11,000 or like over 510. Okay, so if you see any complicated looking fraction, then you did something wrong. And that's a really good assumption. Okay, so now before we wrap up this section, we'll see a few word problems. Okay, so the compound interest and population problems. So apparently this is not an econ or business class, so we are not gonna go too deep on this, but the compound interest. Okay, so let's focus on that first. So the compound interest, so for those who plan to major in business or accounting, you might have already seen or heard the term compound interest, but that simply means the interest is gathered not only on the initial investment, but also any of the previously accrued interest. But that's not the point. So why are we seeing this here? Because the compound interest formula is this one. And as you can see, what do we have? Exponent, right? That little nt. So which is why we study it here. Okay, so now there are 5 letters, A, P, R, and T. And each letter means something. So let's start with the letter T. So I guess you can even guess what T stands for. T is the popular symbol for the time, right? Okay, and now this time is represented in years. Okay, years. And now let's go to A. Okay, so A is the future amount. So A came from the word amount. And amount is in money, right? Dollars. Okay, and this future amount is after T years. And now P is the principal. And what does that mean? It's the present value, right? How much you invest right now, today, right? Okay, so this one is the present value, which is once again in money, right? Okay, and now any interest carries with what? Interest rate, right? Okay, so that is the letter R, interest rate. And now usually interest rate is represented in what? Percent, right? Remember that? Okay, so that's the usual representation, but here it is in decimals. Okay, so what does that mean? You have to know how to convert percent into a decimal, right? Okay, so let's see how well you remember. 3.4%. What is its decimal representation? Don't say 3.4. It's because it's a decimal. Okay, not that decimal, but how can you drop the percent and represent it as the equivalent decimal expression?
Move the decimal left 2 spaces.
Right, move the decimal point to the left 2 spaces. Remember that? So what do you get? 1, 2. So 0.034, right? Okay, so that's the value that you have to plug it in to the formula, not 3.4. Okay, and now N is the number of periods in 1 year. Okay, so now everything is pretty easy to identify. What can be tricky is to identify the value of N. Okay, so how do you identify the value that needs to be used in N? And that is used in this next remark. So to find the values of N, look for these specific phrases in a problem. Suppose it says the interest is compounded daily. Okay, daily. What has to be the value of n? 365, right? Yeah. Okay. Now, sometimes people say, well, what about that, like, February 29th, which will have 366 days? Oh, okay. We don't consider that special cases, like which comes like once in every 4 years. Okay. So just typical number of days in a year. Okay. And then weekly. So that means n is equal to 52, right? Okay. Yeah. In the past, someone said like 71 or something. I'm like, where are you? Like, where are you coming from? Like, you are not from this earth, because as long as you live on this earth, which all of you are, everyone will agree that there are 52 weeks in a year. But yeah, if you think differently, then you should reveal your identity pretty soon, because now you cannot hide your identity, which is like you are alien. Anyways, so compounded monthly. So that means n is equal to 12. And now, compounded quarterly, what should n be? 4, right? Yes. Okay, it's not 3, right? Because there are 3 months in a quarter. And now, semi-annually. What does semi-annual mean?
Twice a year.
Right? 6 months, right? So that means n is equal to what? 2, right? There are 2 periods of 6 months, right? And now, annually means what? N is equal to 1, right? Why? Because there is 1 year in a year, right? Yeah, obvious, but it is the case anyways. Okay, so now here, as you can see, the smallest unit that we are dealing with is days. Okay, but can the interest be compounded less than days? So maybe like hourly. And what about per minute? Per second? Less than a second? Is that even possible? Oh yes. Continuous compound interest. Okay, so for this one, you will see the phrase compounded continuously. Okay, compounded continuously. So if you see this phrase, you know you have to use the different formula, not one of, or like not the previous one. You must use this one. A is equal to, so sometimes people say PERT, P times e to the RT. Okay, and here be careful with PEMDAS. We do e to the RT first and then multiply P in front. Okay, and now what does that E stand for? E is the natural number. Okay, so here the compound interest formula has 2 formulas. One, this one, and the other one, the previous one. And now, what can be scary is memorizing these 2 formulas. Okay, although I memorize them, but it's not expected that you have to memorize it as well. So, go back to this previous page. This compound interest formula, also the continuous compound interest, this one will not be on the final. On the final. But will it be on exam 4? Yes. Okay, and since this one is not on the final, you do not have to memorize this formula or this formula. Okay, so what do you have to know then? So first of all, what I will do, okay, what I will do is on the exam day, I will give you these 2 formulas, okay? I will give you these 2 formulas, but then I'm not gonna write down what each letter stands for. and which formula has to be used on which problems. Okay, I'll just give you these two formulas, and you have to choose which formula to use and which number goes into which letter. Does that make sense? Okay, again, this one is not on the final either. Okay, this whole continuous or compound interest formula thing is not included on the final, but it will appear on exam 4. Okay, and I will give you these two formulas, but you have to choose which formula needs to be used where. Okay, so let's practice. So there are 3 compound interest formula problems, and in my view, this problem is the most important one. Okay, but the reason that I'll do the other 2 problems is because you will see similar problems in the homework. Okay, but there's a reason that I put a star here on this problem number 4 only. Now, find a future value of a $2,000 investment after 6 years if it is earning an annual interest rate of 7%, which is compounded part A, quarterly. Okay, so now here, which formula do we use? That part or the not so part one? Which one do we use? This one or this one? This one, right? Yeah, because remember, this one is only for compounded continuously, right? Yes. Okay, so we have A equals P times 1 plus R bar N to the power NT. Okay, so now, based on how this problem is written, do we know the value of A? The future amount. Do we know it or we don't know it? Okay, yeah, we don't know, right? Now, do we know the principal? The money that we put in right now. And what is that? 2,000, right? Okay, and now, do we know R? And what does R mean? Interest rate, right? And yeah, what's the interest rate? 7%, right? But do we use 7 for R? No. What do you have to do? Convert this into a decimal, right? So what do you do? 1, 2. 0.07, right? Okay, remember you must convert percent into a decimal. If you don't, you will get the wrong answer. And then, do we know the value of N? What's the value of N? 4. Do you see why? Compounded quarterly, right? Okay, so N is equal to 4. And now, do we know the time? Yeah, which is what? 6 years, right? So 6. Okay, so plug them into the formula. So what do you get? A is equal to 2,000, and then parentheses, 1 plus 0.07 over 4 to the power 4 times 6, right? Okay, so people usually get that. And then they stumble. Where? They cannot, some of them, not everyone, some of them cannot evaluate this expression properly. Okay, so here is my recommendation. Number 1, do the exponent first. Okay, you can do it by hand or in your brain, because if you don't know what 4 times 6 is, then I guess you should go back to many years ago, right? Anyways, so you can do it in your brain easily. So that is what, 24, right? Okay, and now you punch in this whole thing into your calculator. How? Just literally punch in, like plug in all of these numbers. Okay, type as it is. So where's my calculator? Okay, so now yesterday I think I've used the graphing calculator. So now let me use this, okay, the scientific one. Okay, So again, if you have graphing calculator, that's fine. You can just type in exactly the way it's written. Okay, so 2000, oops, 2000, there we go. And then it says parentheses, so you put parentheses. Okay, and then 1 plus 0.07 over 4, so what does that mean? 0.07 divided by 4, right? And then you close it. Okay, and now the exponent is 24, right? So what does that mean? Exponent symbol, which is the like this upper hat thing, right? And then 24. And then hit enter. Okay, so what do you get? So I got 3032.885573 and so on. Did you get that? If you didn't get that, then maybe you did something wrong. Okay, so check your computation. Now, A is what? The amount, which is in dollars, right? That's not how we write in dollars, right? Okay, at least in our country, right? Maybe in different countries, like maybe they have like these many decimals. But our typical monetary system is represented in how many decimal places? Right? So what does that mean? We have to round from where? Here, right? Okay, so what's the answer? $3,032.89. Okay, now sometimes the problem could say express your answer in terms of the whole dollar. Whole dollar means what? No decimal, right? Okay, so that means your answer would be $3,033. Okay, but that's the further instruction in a problem, but here I'll just round up to 2 decimal places. Okay. Okay, so now continuously. Okay, so now here comes the key word. So what does that mean? You know the formula has to change, right? Okay, you cannot use that formula. Okay, you have to use what? This, right? Okay, so what do you have here? So what you need is P, which is same thing as before, right? And then remember, E is just E, right? E is the natural number. And then we have R, which is 0.07, and then T, which is 6, right? Oops, 6. Okay, so here, N is not necessary, as you can see. Okay, and again, here, follow my recommendation, which is do this one first. Okay, now for this one, you may not be able to do it in your brain, or some of you may. So here, no matter what you do, you should get 0.42. Okay, so now you type this number into your calculator. Okay, so 2000 times e to the 0.42. So what does that mean? So 2000, okay, 2000, and then times E. And now remember from yesterday's class, what should I do here to make it even more visible? Maybe that. Okay, so times E, so that means what? Second and then ln, right? Like that. Okay, and then 0.42 here. Okay, so what do you see? $3,043 and then the rounding takes place from where? From 3, right? Okay, so what's the answer? 0.92 cents, right? Okay, so $3,043.92. Okay, so as you can see, what do you notice here? The maximum amount, the future amount is achieved when the interest is compounded continuously. Like it's what? Approximately $11 more, right? And that's why all of the banks do not offer any plan or account whose interest is compounded continuously. Why? Because they want to earn money, right? Okay, that's how they make profits. Okay, so there will be an account or any like investment plans whose interest is compounded like quarterly or monthly or weekly. But I know that there is no account whose interest is compounded continuously because the bank wants to save even $11. Oh, how bad banks are, right? That's okay. Everyone wants to earn money, so we cannot blame them. Okay, so now that's number 4. And now here's number 5. So suppose there's a couple and they have a kid who is 1 year old. Ooh, how young. It's a good time, right? And they want to invest money for their kid's marriage. Okay, so they want to have $100,000 in 240 months, and the investment pays interest 7.5% compounded monthly. How much should they invest now? Okay, so now, first of all, do we use that simple formula or the complicated formula here? This top one, right? Okay, not the PERT, right? Okay, now here, do we know the value of A? The future amount. And this time we do, right? Yes. Okay, what's the value of A? 100,000, right? Yeah, don't ask me why the money is so expensive, okay? Like, that's not me, okay? This is just like random number. Do we know the value of P? No, right? In fact, that's what we are trying to find, right? And now what's the value of R? 7.5%. But remember, you have to use its decimal form. So that's 0.075, right? Okay. And then what do you have? N. So what's the value of N? It says compounded monthly. So that means N is equal to 12, right? Okay. And T. What's the value of T? $20, yes. Do you see why? It's not 240, right? Because it's 240 months. So you have to convert 240 months into years. So that means 20, right? Yeah. If you type 240 into the formula, then that means this kid will get married after 240 years. And I don't know how that's possible. Everyone will be dead by that time, right? Yeah. The kid will die before his or her marriage. How sad is that? Anyways, so it's 20, okay? And getting married in 21, that sounds a little bit early, but I don't know. Okay, anyways, that's not the point of this problem, okay? So now we have to get the right number, okay? So what do we have? 100,000 is equal to P, we don't know, times 1 plus 0.075 divided by 12 to the power 12 times 20. Okay, and now, again, what do we do first? This exponent first, okay, which is equal to 240. Oops, 240. Okay, so now, if you look at this equation closely, like it looks terribly hard, but do you notice that this is similar with something like this? Do you notice the similarity? That's a number, right? And that's the variable which we are trying to find. And what is this? That's just some number, right? Which is ugly, I know. Okay, so what do you have to do? First, get this number and then divide 100,000 by that number, right? Okay, so now let's try to find this number first. Okay, so what do you do here? So you just like type in on your calculator that whole thing, 1 plus 0.075 over 12, okay, with parentheses, of course, because that's what we have at the beginning, 1 plus 0.075 divided by 12, and then raise it to the power 240. 240. Okay, so you should get something like 4.4608 and so on and so forth. Okay, so what you have is 100,000 is equal to P times 4.4608 and so on. Okay, so now one thing that you have to be careful is don't round this decimal. Okay, because if you round this and get like 4.5 or 4.46, your answer will be off. Okay, so how can you like not touch this decimal but still get the precise answer? So first, what you do is divide by 4.4608 and so on, right? So you can cancel this. Okay, but when you do that, what you do is first type 100,000 and then divide it by, and hopefully you have seen this tool before, the ANS tool. Okay, so how can you achieve the ANS? Press second and then the negative sign. Okay, so here it's second and then the negative sign is right there, right at the bottom, like that. Okay, so this ANS tool takes the number that you got in the previous spot or previous step. Okay, so if you use this ANS tool, that whole decimal will come down here without being rounded. Okay, so you should get something like this. Okay, again, like I'm not saying that's the answer, but it's the ANS tool. Okay, so you should get P to be $22,417 and by rounding 42 cents. Okay, so the rounding does not take place until the very end. Okay, it's expensive amount. Okay, I know, but you know, this is a fake problem, so whatever, like anything can happen. Okay, so now that's number 5. And now number 8. So this one is, or number 6 actually. So this one is kind of weird and the trickiest among the 3 problems. So if $5,000 is invested with the interest compounded weekly, what has to be the interest rate so that the money grows to $7,000 in 2 years? Okay, so now for this problem, again, notice that we are using this the top formula, right? Because it doesn't say compounded continuously. Okay, so here, do we know the future amount? Yes, which is what? 7,000, right? Do we know how much we invest right now? 5,000, right? Do we know the interest rate? No. What's the value of n? It says compounded weekly. So that means what? 52, right? And how much time do we need? 2 years, right? Okay, so we have 7,000 is equal to 5,000 times 1 plus r over 52 to the power 52 times 2, right? Okay, and now we have to get the value of what? R. So what can we do here first? We'll do the same thing. Always do exponents first. So this is equal to what? 104, right? Okay, so now here comes the tricky part. What do we do first to get R by itself? What needs to be the first step? This can be tricky. So here we have to remove several things. We have to remove 5,000, we have to remove 104, and then this 1 and 52. What can be removed first, and what should be removed first?
Is it divide by 5,000?
5,000 first, yes, and it's division, okay? So divide by 5,000 needs to be done first, okay? So what does that mean? 7,000 divided by 5,000. And if you use your calculator, okay, I'm not gonna show it here, you should get 1.4. So 1.4 is equal to 1 plus r over 52 to the power 104. And now, what do we remove next? 152 or 104? So this can be tricky. So let me just tell you the answer right away. We remove 104 next. But now the question is, how do we remove 104? So for example, if we had x cubed equals 8, how do you remove that 3? So you take the cube root, right? But in terms of the exponent, what does it mean? That, right? Okay, then you can just remove that, right? Now, does it tell you the answer for this one? How do you remove 104? Raise each side by what? By what power? That, right? Okay, so that means we have 1 over 104, 1 over 104 like this. Okay, then these two will cancel. Okay, so now when you do 1.4 to the power 104, you have to be a little bit careful, okay, because depending on what kind of calculator you have, so here, for my calculator, I can do 1.4 to the power, and then I can type 1 over 104 like this, and then I get this number, okay, like 1.0032 and so on. But if you don't get this number, then what you have to do is 1.4 and then this exponent symbol here, and then parentheses 1 over 104 like this. Okay, so you must put parentheses over this exponent 1 over 104. But for some calculators like mine, or maybe some of yours as well, you don't have to do this, okay? But you must get 1.0032 and so on, okay? So here you have 1.0032 and so on and so forth is equal to 1 plus r over 52, okay? And now it's fairly easy to see what needs to be done next. So there are only two more steps. What's the next step? Subtract 1. And then to remove this denominator, what do you do? Multiply by 52, right? Okay, so let me just do these all in once. So what do you get? Oops, what do you get? So r is equal to, so first from here you subtract 1. And then you multiply this by 52. Okay, so you should get 0.1685086 and so on. Did you get that? Okay, so it's 0.1685 and so on. Now, R was what? The interest rate, right? Which is typically represented in what? Percent, right? But this is not 0.1685%, right? So what do? Do that, right? Okay, so what's the answer roughly? 16.85%, which is kind of insane interest rate, right? Yeah. Well, okay, so again, the reason I did this problem and the one before, like the one-year-old kid's marriage, was because you'll see some of these like similar ones on the homework. But the main thing, the main problem about this compound interest formula is the very first one that we did, finding the future values. Okay, and now the one last remaining problem. The world population in millions closely fits the function 6,084 times e to the 0.012 t, where t is the number of years after 2000. Estimate the population in 10 years from now, year 2030. Okay, so here, what do we do? So here we have this function, and we have to plug in some number to t, right? Now, does that mean we plug in 2030 into t? No. Yeah, because if so, what does that mean? It's the population in 2030 years after 2000, right? Which is, yeah, will this Earth even exist back, like in the year 4030? I don't think so. Anyways. Yeah, certainly like we will not exist, right? Like we'll all be dead, okay? But what's the value of t? 30, right? Okay, and now we plug this in to the function, right? Okay, so what do we get? 6,084 times e to the 0.012 times 30, right? Okay, so we have seen this expression before. We do this one first. Okay, so we get 6084 times e to the, what is this? 0.36, is that right? Okay, like you have to maybe use your calculator, but yeah, I think that's right. Okay, so now you punch in this number to the calculator once again. So 6084, and then e to the power 0.36. Okay, so it's 8720 point, maybe let's round up to 2 decimal places, so 0.38. Now, what is the unit for this decimal? Millions, right? Yeah. There can be like about 8720 people in the earth, like in 2030, right? Yeah. Like most of the people have to die by then. Yeah, like yeah, somehow like all of the problems are kind of tragic, but I didn't mean to. But it's millions, right? Okay. Yeah. So what does that mean? It's a little over like 8.7 billions, right? Which makes sense. Like right now we have what, 7.4 billion or so? So that sounds a bit normal, okay? Okay, so that is kind of simple problem. Any questions on these word problems? Okay, so now that's it for 4.2, and now, oops. And now I will combine 4.3 and 4.4 in this one lecture note because all of them deal with so-called log. Okay, now maybe some of you have seen or heard about the log or logarithm, but let's have two introductions. Okay, like some people who have seen the log, they typically don't like it, but it's actually not that terrible. So fill in the blanks. Part A. This is part A. And then part B. And then C is this. Now, maybe you can plug in these blanks and tell me what the answers should be. So what's the answer for part A? 2, and then blank is 8. Okay, and now, what is the number on the second part? So maybe you need some hint. Remember 9 is 3 squared. So we have 1 over 3 squared. Does it remind you anything? What has to go into the second blank?
-2.
-2. Okay, -2. And now e to the blank is 1. That should be easy. What should blank be? Say that again.
-e.
0. Okay, because anything to the power of 0 is 1. Okay, so now what have we found on these three problems? We found the exponents, right? In fact, that's what we found, the logarithm. The log is finding the exponents. Okay? Now, here's the second introduction. Addition. And here, the two-sided arrow means opposite or inverses. Okay? So what does that mean? The subtraction is the opposite or inverses of the addition, and it goes the other way as well, right? And then multiplication. What is the opposite or inverses? Division. Okay? And then exponential expression. What is its inverse? The log. Okay, so the logarithm and then the exponential expression are inverses. They're opposites. Okay, which is why we cover this log after we cover exponential expression. Okay, so here are the two introductions. And now, here is the crucial fact, which will appear like a million times, not only in these two sections, but also in the next section as well. So we have y equals log and then subscript a and then x. Okay, so this is same as a to the power y equals x. Okay, so now let's look at this log subscript ax. Okay, so this thing. Here, okay, so I guess first, before we look at this, what is the name of this a? It's the base, right? Remember that? And what's the name of this y? It's the exponent, right? Okay, and now, guess what this little a is called? Also the base. Okay, but now this is the base of not the exponential form, but the log. Okay, so we say this is the base a logarithm. It's not base c logarithm, okay, it's base a logarithm. Okay, because that little thing is called the base as well. Okay, so now we have a few crucial deductions from this fact, okay, which is, so that's the base of the exponential form, and this base is same thing as the base of the log, so we always say base goes to the base as well. Okay, so that's pretty easy to understand. Base always goes to the base. And now, the exponent, okay, or power. So exponent is y, right? And now, where do you see y on this equation or expression? Here, right? Okay, so the exponent is written as the result of the log. Okay, so base goes to the base, that's pretty easy. And then the result of the log becomes the exponent. Okay, and then once you identify the base and the exponent and see where they have to go, you can see the remaining thing, which is x, has to go, which is right here. Okay, so identify the base and then the exponent, and then everything will follow. Now, the condition for the base of the logarithm is it's positive, but it can't be equal to 1. And now, have we seen this condition before? And the answer is yes. Where have we seen it? It was the condition for the base of the exponential form a to the x. Remember that? And it makes sense, right? Because base always goes to the base, so it has to have the same restriction, okay? And now, we can replace the y on the left-hand side by f of x. So what do we have? F of x equals log sub ax. And this is called the logarithmic function. Okay, which we will not study in this course because this is not that important. But if you take the future math courses, say calculus or trigonometry, you may see this logarithmic function. Okay, but we are not going to study this in depth here. Okay, now, the fact is that we cannot omit the base of the log. So that means this little a here, that cannot be removed. That must stay, except for two special logs. Okay, except for two special logs. And these come on the next page. So here are the special logs. So suppose base is equal to 10. Okay, then what do we have? Log sub 10x, or we have base 10 logarithm, right? Now, when the base is 10, nobody says base 10 logarithm. Instead, people say, or first, people write, okay, so let me slide this paper a little bit, okay, right here. So we write just that, log x, okay? So what does that mean? Compared to this original form, what is different? The 10 is dropped, right? Okay, and we just have log x. And its name is not base 10 log. Its name is the common log. Okay, I don't know, honestly, why it's called the common log. Maybe because 10 is a common number? I don't know, okay? But that's just the name, okay? Common log. It's not my own representation, okay? It's just the official name. It's the common log. And now, the good thing about this common log is your calculator has this, okay? So, let's see. Now let me grab this calculator, okay? So now, where is the common log? So, right above ln, you will see this log, okay? And this is the common log. And you can see why. Right above this log, you will see 10 to the power x. And same thing for this one, okay? You will see log right here, and then right above it, you see 10 to the power x, okay? So that's why the base is equal to 10. Okay, so use the log button on your calculator. And now, the second special log is when a is equal to e. Now, what does e mean? Natural number, right? Okay, so when that's the case, we have log sub ex, or its base e logarithm, okay? But again, that's not the way to write. So how do we rewrite this base e log? So the problem is, if we drop this base, we have log x, but that's same thing as the common log, right? So we cannot use log, so we have to use something else, which is ln. Okay, and now, what is the name of this ln? Okay, it's same thing as base e log, but nobody calls that way. The official name is the natural log. And what's the reason? The base is the natural number. Okay, And now, also your calculator has this natural log. Where is it? Right here. Where is it? On your graphing calculator, if you have it. Right here. Okay. And right above this ln, you will see e to the power x, right? And that's the reason. E is the base. Okay. So use the ln button on your calculator. Okay. So these are the basics of the log. And of course, we'll see a lot more in the future. So now let's work on a few problems. Write each in the equivalent logarithmic form. Okay, so the thing is, usually this kind of problem gives trouble to a lot of people because they just don't know what to do. Some of them, okay? So we have 4 squared equals 16. Okay, so what does this mean? This kind of problem means use the previous fact. And what do I mean by previous fact? It's this one. Okay, so you must use this fact. And notice that this allows us to convert from, this logarithmic form and then into exponential form. And it's going back and forth, right? So we have to use this fact on this problem. Okay, so now how can we use this fact? So remember these two things, these two, okay? Base always goes to the base, and then the exponent is the result of the log. Okay, so first, what do you do? By just looking at this expression here, can you identify the base? 4, yeah, right? Okay, and remember base always goes to the base, so we have what? Logs of 4, right? Okay, and now, what is the exponent here? Exponent is 2, right? And remember, exponent becomes what? The result of the log, right? Okay, and remember the result is always written where? After the equal sign, right? Okay, here, which is after the equal sign, right? Okay, so you have what? 2 equals, right? Okay, so now you took care of 4, you took care of 2. What's the remaining number? 16, right? Where should that go? And where is the remaining blank? Here, right? Okay, so that's it. Okay, now the thing is, you can also write that result, which is the 2, on the other side of equal sign. Okay, and I will typically write like this, but this one is also fine. Okay, so again, identify the base and then the exponent, and then the other thing will follow. And now part B, a to the 3rd power equals 27. Okay, so when some people see this, they say, oh, yeah, I get the answer. A is equal to 3. Good job. Unfortunately, you haven't done any inches of this problem. Okay, yes, I'm impressed by your brilliance, but that's not the point of this problem, right? You have to write this into logarithmic form, which you didn't even write an ink of it. Okay, so what do you do? Well, do the same thing. here, what's the base? What's the base? A, right? Yeah, okay. Which we don't know what A is. Well, yeah, A better be 3, but that's not the point, right? So A becomes the base of the log. So what do you have? It's log sub A, right? Okay, it's not like log. And what do we have? Exponent. And what's the exponent? 3, right? And that becomes the result. So what does that mean? It's written after equal sign, right? Okay, so we took care of A, we took care of 3. What's the remaining number? 27 has to go here. Okay, and that's it. And now part C. E to the negative 3 is equal to A. Okay, so do the same thing, base, which is E, and that becomes the base of our log, right? And then what is the exponent? Negative 3, that becomes the result of our log, right? Okay, so what do we have? We have log sub E, and then negative 3 will be the result, so it needs to be written on the other side of equal sign. Okay, so we took care of E, we took care of negative 3, and what's the remaining thing? A, right? So A goes into here. Okay, now, is this the answer? And the answer is not for this problem. Why not? Because how can we rewrite this thing? ln, right? Okay, so this is the natural log. So we must rewrite this into ln A is equal to negative 3. Now, the common mistake that people make is writing this subscript E below ln. Is this right? No. Okay, so whenever you write ln, either write ln or just write log sub E, but try to avoid log sub E, okay? Use ln, okay? So yes, this is understandable mistake, but this is wrong. It's just ln A equals negative 3.
So does it not matter that the exponent is negative? Like you don't have to change that if you're going from one form to the other?
When exponent is negative? What do you mean? Exponent can be negative. Yeah, exponent can be negative, okay? But yeah, like all I'm doing is just like the conversion of this expression into this like logarithmic form. Yeah, okay, and like don't try to like question yourself about like, is this even true or something? Like that doesn't really matter here. Okay, so as long as like you have identified your base and exponent and you have placed them properly in the right spot, you're good to go. Okay, so this might be false. Well, actually, like I know the result, like this is true, like this is possible. This is possible, but as long as you identify your base and exponent, you're good to go. Okay, so we have converted exponential form into logarithmic statement. And now, can we go backwards? Which means, given the logarithmic form, can we convert into equivalent exponential form? And the answer is, oh yeah, why not? Okay, and how do we do this problem? Do the same thing, use the same fact. Okay, But of course, we will apply it in a slightly different way. Well, first, what is the base of this logarithmic form? One half, right? Yes. So base is always this like small number here. So base is 1/2. And remember, base always goes to the base. And now, be careful. This time, we start from the log statement, and we want to write the equivalent exponential form. So what does that mean? We will have 1/2 as the base, right, of the exponent or exponential form. And now, instead of looking at the exponent, what are we looking at here? Oh, we have a cat today. Okay. Hello, kitty cat. So now we look at the result, right? Okay. What's the result here? -3, right? Okay. So we just go a little bit backwards. Okay. So the result is -3, and that will become what? The exponent, right? Okay, so what do we have? 1/2 to the power -3. Okay, so we took care of 1/2, we took care of -3, and now we are left with that 8. So how should we write 8? Equal sign and then 8, like this. Okay, so that entire thing is the answer. Okay, so instead of going from exponent to the result, we go from result to the exponent. Okay, so that's the only difference. Everything else stays the same. And now, part B. Can I go to the next page? Okay, so now part B. So log 1/1000 is equal to -3. Okay, so first what do? We first identify the base, right? Now here, the base, is the base equal to 1000? No, the base is missing, right? Does that mean we are in trouble? What is the base here? 10, right? Yes. Okay. Do you see why? Because we don't see the base and we have log, right? So that's the common log, right? Okay. Whose base is equal to 10. Okay. And 10 becomes our base. So we have 10 to the whatever power, right? And now we look at the result, which is -3. And that becomes the exponent, right? Okay, so we have 10 to the power -3. So we took care of -3 and we took care of this base. And we are left with what? That 1/1000, right? So what does that mean? Equals 1/1000. Okay, that's it. And now, part C, ln1 is equal 0. Now here, what's the base? E, right? Yeah, because ln is what? The natural log, right? Whose base is equal to what? E, right? Okay, and this base becomes the base. So we have what? E, and then to the power something, right? Now, what should this power be? Zero, right? Because that's the result, right, of the log, which is 0. So we have e to the power 0, and the remaining thing is 1, so equals 1, right? Okay, so that's the answer. Okay, so base always goes to the base, and then the exponent is the result of the log. Remember these two things, okay? So any questions on this convergence? Okay, so now, just like we saw basic exponential equations in the previous section, let's look at basic log equations, okay? And we will look at not so basic log equations in the next section, 4.5. But what's the strategy of solving these basic log equations? We use the previously mentioned fact, which is what? This is same thing as this. Okay, so what's the point? We convert log equation into the exponential form and then solve. Okay, so that will be the entire task. So let's look at a few problems. Number 3, x, or part A, x is equal to log sub 36 square root of 6. Okay, now please don't say, oh yeah, x is isolated, so that's the answer. Well, yeah, but now you have to simplify that right-hand side. Okay, so now let's try to convert this whole thing in terms of this exponential form. Okay, so now there are lots of numbers and letters, so things can be tricky, but remember, the basic scheme remains the same. So first, how do we convert this into exponential form? Number 1, base, right? What is the base here?
36.
36, right? And that becomes our base. And now, what is the result of the log? X, right? And that becomes the exponent. Okay, so what does that mean? We have 36 to the power x. And we took care of that, we took care of that. So what's the remaining thing? Equals square root of 6, right? And now, have we seen this kind of equation before? In the previous section, right? So what's our goal now? Okay, so now remember what we did at the beginning of the class today. So what's the goal? We have to have the same basis, right? And then we can set exponents to be the same. So here, 36 to the power x. So first, 36 and 6, are they related? Yeah. So what does that mean? 36 is what? 6 square, right? And now what about square root of 6? 6 to the what power?
Half.
1/2, right? Yeah, remember that. So what do we have? 6 to the power 2x is equal to 6 to the power 1/2. And so we have the same basis, right? So what does that mean? We have exponents are the same, right? So 2x is equal to 1/2. Okay, so divide by 2. So what do you get? It's a half of a half, right? So what is that? Quarter, right? Okay. So once we convert any basic log equation into exponential form, we can just use what we have used at the beginning of the class today. Okay, so now part B. Log x 16 over 9 is equal to -2. Okay, so once again we convert into exponential form. So what do we have? The base is equal to what? X, right? And that goes to the base. And what's the result here? -2. Okay, and that becomes the exponent. So what's the conversion? X to the power -2 is equal to what? 16 over 9, right? Okay, and now we have seen this kind of equation before. Okay, so let me see if I can pull that out. Right there. Remember that? Okay, so what did we do here? We rewrote x to the power -2 in terms of 1 over x squared, and then we used cross multiplication. And then we used the square root method. Remember that? Okay, so can we do the same thing here? Yeah. Okay, so this is equal to 1 over x squared is equal to 16 over 9. And then cross multiplication, that gives us what? 16x squared equals 9, right? Okay, and now, can we use the square root right away? Or can we take the square root right away? No. What do we have to do first? That, right? Okay, so we have x squared equals 9 over 16. And then we can take the square root, right? Okay, so what do we get? X is equal to plus minus, don't forget plus minus, and then 3/4, right? Okay, so now for the previous problem, which we did on this problem, we didn't remove the negative number. Now, for this one, do we have to remove the negative number? And yes, we do. And what's the reason? Where is x at the beginning? It's on the base, right? And remember, what is the condition of this base? It's positive other than 1. Remember that? Okay. So remember, in that previous problem, x was not the base, but this time x is the base of the log. So here we have to cross out the negative number, okay? And the answer is just positive 3/4. Okay, so the negative number doesn't work. Okay, because x was here the true base. Okay. And now, part C. Log 16x is equal to 3/4. Okay, so again, we convert. Okay, so convert. So what's the base here? 16, right? Okay, and that becomes the base. And then, what is the result? So the result is 3/4, right? And that becomes the exponent. Okay, so what do we have? We have 16 to the power 3/4 is equal to x, right? Okay, so now, what do we do next? So here we have 16 to the power 3/4. Is there any way to rewrite this? Okay, so now rewrite this one. So how can you rewrite this? So can you first convert into radical form, like some kind of root? And what kind of root do we have? Cube root or fourth root? Fourth root, right? And what do we have under this fourth root? 16 to the power 3, right? And now, do you have to compute 16 cubed? No. What do you have to do first? What can you do on that exponent 3? Do that, remember that? So we have fourth root of 16 to the power 3, right? And now, why is this useful? What's fourth root of 16? Two, right? Yes. Okay, so we have 2 cubed, which is equal to 8. Okay, so 8 is the answer. Okay, so now we did the hard problems, and now the 2 remaining problems are not too bad. So on the next page, so we have log sub 1/2 x plus 3 is equal to -4. Okay, so here, again, we convert. So what's the base? It's 1/2, right? Okay, so base goes to the base. So we have 1/2. And then what's the result? That's the result, right? Okay, and result becomes the exponent. So we have 1/2 to the power -4. Okay, and then the remaining thing, x plus 3, right? Okay, so now we just have to solve it. And now, what is 1/2 to the power -4 equal to?
$16.
16, yes. Do you see why? Okay, you can drop the negative sign, and then you have to flip the fraction, right? So it's 2 to the power 4, which is equal to 16, equals x plus 3. So x is equal to 13. It was indeed simpler, but of course you had to know this conversion. And now, part E, log sub x plus 3, 6 is equal to 1. Okay, so now convert this into the logarithm or the exponential form. So here the base is, x plus 3, and then 1 is the result, right? Okay, so we have x plus 3 to the first power is equal to 6. And now, what is x plus 3 to the first power?
X plus 3.
So it's x plus 3, right? Yeah, anything to the first power is itself, right? So x plus 3 is equal to 6. So x is equal to 3. Okay, so the last two problems were fairly simple. Any questions over these basic log equations? Okay, so now the core of these two sections is not these above facts. It's the rule of logarithm. And then this is so important that it will reappear like a lot of times on the future problems. Okay, so we will fill in these blanks and that will be it for the day. So rules of log. Number one, log base, so base A logarithm applied to A. Okay, so these two numbers are the same. When they are the same, no matter what your A is, it's equal to 1. Okay, and now base A log applied to 1. Okay, so now 1 is here. In that case, it's equal to 0. Okay, and although these two things may look weird, it's actually pretty easy to see why it has to be 1 and 0. When you convert this into exponential form, what do you have? A to the first power equals A, right? Okay, so that's why it's equal to 1. And here, it's what? A to the power 0 equals 1, right? Okay, so yeah. And now, fact number 3. So this is the real beauty of the log. When you have a mixture of log and exponential form, so what do you have? M to the power R is within the base A log. In that case, it's equal to R times log AM. And what does it mean? Take the exponent, which is R, and bring it all the way to the front of the log. So bring down the power or the exponent to the front of the log. And that is the powerful thing about this log. It allows us to mobilize the exponent. Okay, so otherwise, like in other cases, we cannot move the exponent. But if we take the log to the exponential form, we can move it and put it inside or put it in front of the log. Now, in particular, if we have log A to the power R. So what does that mean? We can still move the exponent and put it in the front. So we have R times log A, right? And now, what is log A equal to? Because of fact number 1, it's 1, right? Okay, so this is R times 1, which is equal to R. Okay, so when these two things are the same, the answer is just the exponent R. Okay, and now conversely, if the logarithm is inside the exponent, so we have A to the power log AM. So again, what do you notice here? The two bases are the same. In that case, you can cancel A to the power log A entirely, and the answer is just M. Okay, and here be careful, it's not A to the power M, it's just M. Okay, so a to the power log sub a, they cancel all together, and it's equal to just m. Okay, not a to the power m. And then rule number 5 and 6, they are also important. So you can say, like, what is not important? Oh, nothing. Everything is important. Okay, so log a and then m times m. Okay, so there is a product inside the log, and this is equal to, so what seems to be the case, whenever you have the product inside the log, you seem to be able to distribute this log sub a, and we have log a m times log a n. And that's actually false. It's log a m plus log a n. Okay, so what does that mean? You now have the summation of the logs. So why? What's the reason? Why does the product change into the addition sign? Remember from our earlier introductions, which was right here, we saw that logarithm is same thing as the writing the exponents. So was there any rule of exponents that allows us to add the exponents? And the answer is yes, there is. Okay. So when we have a to the m times a to the n, it's equal to a to the power m plus n. So when we multiply two exponential forms, we will add exponents. And that precisely corresponds to this. Okay. And now, can we subtract the logs? And the answer is yes. So what should be the form? So when can we subtract exponents? So think about it. When can we subtract exponents?
When there's division in the log.
Division, yes. Okay, so we have log a m over n. Okay, and again, what's the reason? There was another rule of exponents which goes like this. When we have a to the m over a to the n, it's equal to a to the power m minus n. Okay, so again, the rule number 5 and 6 says the product inside the log, this is same thing as the sum of logs. Okay, and then when we have a division within the log, that's same thing as the subtraction of logs. Okay, so remember these two conversions, and also other formulas are important, but remember these, okay, especially because they will appear like a lot of times, even on chapter or section 4.5. Okay, so these are the rules of logarithm, and then tomorrow we will apply these rules of logarithms to the problems. And let's see. So I wanted to finish these two combined sections, 4.3 and 4.4, but obviously we couldn't finish it. So this afternoon, let me think about whether I will move the exam 4 to Friday, which is officially not our class day, but I mean, like you just have to show up, quote unquote, show up on Friday at the one of the 3 time slots just to take the exam. But I'll have to think about the remaining problems and remaining sections. and see whether they are difficult enough so that you need more time to study, or we can just finish everything tomorrow, and then you can just study for a day and then take the exam. But I'll have to think about it. And then if I end up changing the exam for date, I'll have to adjust the homework due date as well, which all of them are due tomorrow night at this point, but all of them have to be due Thursday night, but I'll have to think about it. So I'll let you know via email, so check your email this afternoon. Okay? So that's it for the day, and I will see you tomorrow at 10.